the Electrical Engineering Department. I warmly welcome our eminent speaker, Dr. Ashutosh Giri sir. He is an assistant professor at Department of Electrical Engineering, GEC Bharuch. He has completed his PhD from SCET Surat in 2020. He has more than 13 years of teaching experience. He is associated with many professional bodies and worked as a technical program committee member and organization committee members, and also a special session organizer. He has also served as a technical program committee member in conferences organized at Scientific Federation of Dallas, USA, and Kenitra, Morocco. He has done many projects and consultancies worth rupees near about 50 lakhs in rupees. He has published more than 40 papers at various journals like IEEE Transactions, IET, Wiley, etc., and conferences at national and international level. He has also co-authored one book chapter which is published in Springer publication and edited 2 books for each of CRC Press, Florida, and Springer Nature, Singapore. He received many awards and honors at national and international levels. He was nominated Best Researcher of the Year 2019 at Electrical Engineering Department, SCET Surat in 2019. So today he will share his experience on role of intelligent techniques in microgrid. Sir, we are delighted to have you with us. Thank you, sir, and over to you, sir.
Thank you very much, entire team of this FDP, for giving me this opportunity to present myself in front of your esteemed colleagues, participants, and all. Now, let me share my contents first. Is my slides are visible?
Yes, sir.
Okay. I hope so. You all are getting my contents from this end. Now, this is one very important FDP, microgrid, a path to sustainability. And we all know for organizing any FDP, it is very hectic task. That's why we all are thankful to the FDP team. And the topic is very relevant to the current scenario of the power system. We all know our conventional grid, it is, we can say, very complex. Operational problems are there. Sometimes if failure occurs, it affects entire system. That's why, and more or less, our conventional grid is dependent on the conventional generations like burning of coals and some part of nuclear energy. We are least dependent on the renewable energy. That's why in current scenario, when we are discussing, whole world is discussing about the global warming, about the environmental pollution, and about some other climate changes. Microgrid is a very relevant, you can say, area for research and for power generation. Mostly renewable energy use is more in the microgrid concept. We all know for our country, the country like India, there is no limited, you can say, the solar energy, wind energy, all are available in abundant in nature, right? We can tap the energy. Still we are very much lagging as compared to European countries and American and Canadian. We are very, you can say, lagging in this sector. We are our if you see the share of the energy, it is very less. We are discussing here a very important topic, And my talk is role of intelligent techniques in microgrid, because we all know, suppose whatever the sources are there in the microgrid for power generation, they are intermittent in nature. Suppose we are discussing the wind, we are discussing the solar. There are two major sources of the microgrid power generation. The wind is also, sometimes it is available, sometimes it is not available. Solar, sometimes it is with full intensity, sometimes there are clouds in the environment, we are not getting the irradiation 100%. That's why they are said as intermittent nature. And if we are not providing any kind of control to the power generation, the power generation will be useless. That's why role of the control techniques in microgrid operation is very, very important. And here there are so many control techniques like classical, adaptive, intelligent, artificial neural network based, IoT based. There are so many, but my work basically based on some intelligent techniques. That's why we are discussing here the role of intelligent techniques in microgrid. Now, this will be the overview of the presentation. First of all, we will discuss what is microgrid, then what are the common architectures, then what may be the configurations. There may be so many configurations, but here we will discuss some configurations. The people who are working in this area, they can take any configuration and do their research. Then what are the various research scopes, then various type of control algorithms, and out of that we will discuss here the intelligent control algorithm. Intelligent adaptive controllers used as a primary control in microgrid, and basic principles of intelligent adaptive ATAL control algorithm. Then we will discuss some more you can say adaptive control algorithms, and then I will try to show some simulation results. And then the important part of this presentation will be how to develop your microgrid prototype in the laboratory environment, and what are the various challenges, what are the circuits by which we can validate our any control algorithm, right? And then I will show some experimental results for your reference, so that if you are doing something, you must know what are the expected results. So we will discuss almost one package of microgrid operation, and I hope so you all will enjoy from this session. You will learn something, and this is not one-sided discussion. This should be the two mutual discussion. I am also learning something from you people. If you are asking questions, I will be happy to share my experience. Now, FDP is based solely on microgrid operations, controls, and architectures. You may have heard the name and introduction of microgrid in the previous sessions, but still I am taking some introductory slides here. The increased predominance of distributed generation resources like we know solar, wind and all, incentives, and the necessity to provide a reliable, secure and clean supply of power to consumers has steered the emergence of new type of power subsystem that is known as microgrid. So this word is not new for anyone. It is very popular word, microgrid. And what are the various things involved to form the microgrid? We all know microgrids addresses concern about stability and power quality with self-sustainability and fault tolerance. They do, however, raise new issues and challenges regarding effective power system operation and control. The interconnection of large number of renewable energy sources to the grid causes problems of control and stability. Suppose if we are taking two sources in tandem, in parallel, we can say, then there will be the problem of synchronization, there may be the problem of interfacing, because some sources may be dynamic in nature, some sources may be static in nature. We have to understand the concept, how to interface the variety of sources to formulate one microgrid concept. And the problems basically control and stability. and also raises concerns about reliability, power quality, and security. Power quality is very important terminology in any power system concept. Either it is microgrid, nanogrid, or it is mini generation, you can say medium type of power applications, or some distribution systems have higher power side. Power quality is very important because we all are using some sophisticated gadgets in our household devices, and if power quality is poor, if power is not fed to those devices with proper power factor or proper zero crossings, then, or you can say proper wave shape, then it may distort, it may destroy the you can gadgets. That's why power quality is very important terminology. To resolve these concerns, the preferred approach is to view distributed energy sources and their associated loads as a single entity, the microgrid. This is the microgrid actually. Essentially, microgrid is a smaller portion of power system. It accomplishes enhanced reliability of supply, quality of power, and optimal cost of operation, right? So this is a smaller part of the power system, we can say microgrid. It is the operation of microgrid, we all may be knowing, either it is in islanded mode or it is grid connected mode. But here in this presentation, we are very much concerned with the islanded operation of the microgrid. And what is the reason why we are going towards the microgrid? There may be some places who are still not connected from the grid. That's why microgrid generation is very good option for them. So feeding power to remote locations, easy control and operation. We all know microgrid. Suppose if we are planning a very medium or small power applications, there may be one or two sources of some kilowatt, and controlling is very easy. For increasing the renewable energy share, because most of the microgrids are based on renewable energy, share can be increased. No need of regulatory bodies, because still standards are not defined clearly for the microgrid. That's why regulations, if we are working on the standard, if we are working with grid connected mode, you have to follow the grid codes. But suppose if we are working on the you can say islanded mode of operation, no need to follow anything. Less expensive, capital investment is less. For reducing the burden on the grid, it will provide the modernization time of the conventional grid. For reducing the greenhouse emission, for increasing the overall economy, for better living standards, the people who are living at remote places, villages, and if we are feeding them with microgrid, if we are feeding supply by utilizing the microgrid, their standards may be good, living standards may be good. Increases the energy efficiency. Energy efficiency is one very important aspect of any system. In conventional system, almost 10 to 15% losses in the distribution and transmission. That's why efficiency is poor as compared to the microgrid. Peak load reduction, enabling the grid modernization, encourages the third party investor. Yes, actually conventional system is very, we can say, vast and large. That's why the third party investment is difficult in the conventional system. But in microgrid system, people are ready to invest to generate 100 megawatt solar, 100 megawatt wind, like that. That's why third party investment is easier, and that is encourageable. Local control for maintaining power quality and reliability. Power quality, as I said earlier, power quality and reliability, they both are very important term, and they should be maintained. Either you are working at any power level. Suppose you are working at medium power level, higher power level, or low power applications, power quality must be there. Without power quality means we are not utilizing energy properly. Energy efficiency is also dependent on the power quality. Promotion of community involvement in power generation, it is very important thing, because in conventional system there is some passiveness from the load side. But if we discuss the microgrid concept, load side is also became one active element of the system. right? That's why it is community will be involved in the power generation. That means load side is also generating the power, and then if they are having some facility to connect from the grid, they can take the rebate if they are surplus, if they are having surplus power generation. This is one general architecture. There may be so many things in the microgrid. Basically, there is no clear cut. It should be only wind, battery, or solar, or fuel. There are so many sources can be connected in the microgrid. Just a minute. So this is the architecture of general microgrid, where microgrid can include distributed energy sources such as generators, storage devices like battery and flywheel mechanism, etc., and then controllable loads. Microgrids generally must also include a control strategy to maintain. As I said earlier, control is the fundamental part of the microgrid. On an instantaneous basis, real and reactive power balance, these are the challenges, how to balance the power flow in the microgrid. Reactive power balance, when the system is islanded and over a longer period, to determine how to dispatch the resources. Suppose this one is known as, we can say this is the point of common coupling, PCC. Here critical loads are connected. This is the main switch through which we can connect through the grid, right? In my work, basically this part is missing. Only what we will discuss here in this presentation, we will discuss the islanded microgrid. It is not connected from any big network. There are sources like wind turbine, then power electronic converters. These electronic converters are playing the role of you can say interfacing, for interfacing purpose, because battery and wind turbine, they cannot be interfaced directly from the PCC, from the point of common coupling. They must have to interface through some power electronic device which will provide the common type of quantities which are interlinked, which are interconnected. Then solar cell, we all know solar cell is static in nature, wind turbine is dynamic in nature. There is inertia in this system, there is no inertia in the solar system, right? That's why power electronic interface is needed. In every source you can see the power electronic converters like that. This is needed. This is the integral part of the microgrid. And just I have shown here one simple configuration of the microgrid of two sources. There are one, basically I am working on this. This is simple configuration of the microgrid. SCET means squirrel cage induction generator. This is running from the wind turbine, that means wind generation and solar generation, and then battery energy storage system. And then I explained in this power electronic converters. So this is one power electronic converters, and there are 4 legs over here. There are 8 devices, 8 IGBTs. They are forming one bridge configuration, and this bridge is interfaced through PCC. You can see here it is written CPI, common point of interface, but you can say it is the PCC, where load, other source, and this source is connected through the converter. So all these sources are connected at the PCC. That's why this concept you can see here. Suppose if you eliminate, for a time being, if you eliminate the battery and the fuel cell, if we discuss only wind turbine and solar cell, and then through power electronic converters, this is the common coupling, where point of common coupling, where load is connected. The same type of some type similar configuration, but in detail. Suppose here excitation capacitor is needed to excite the generator. Battery is also provided for power storage from the solar, and then this is the one kind bidirectional converter for charging and discharging of this battery. Then capacitor DC link, capacitor is provided at the DC link. That's why it is known as DC link capacitor. And for proper operation of this inverter unit, we have to maintain the constant DC link supply from this point. This is known as in combination, all the switches in combination. This is known as voltage source inverter, VSI. And this is one kind of high pass filter. And these are the ripple filters. Actually, ripple filter is written wrongly here. These are the ripple filters, current ripple filters, and this is the high pass filter. Why high pass filter is used? Why current ripple filter is used? We will discuss in detail. Basically, ripple filter is needed to shape up the current which is coming from the pulse width modulation techniques, and high pass filter is needed to make one to provide one path for the high frequency components which are created. Those high frequency components are coming from the switching operation of this inverter unit. That's why if we are not providing this kind of arrangement, they may be propagated towards generator, or they may be propagated towards load. Both ways, if they are propagating in any direction, they will create some problem. That's why we have to provide some alternative path. This is the that means that's why it is known as high pass, right? High frequency components will be circulated in this. And this is another configuration where a diesel engine is, you can say, running the SCET. Diesel engine, the characteristic of wind and diesel, both are different. Diesel engine is, most of the time they are providing constant power to the generator. But here they may be providing sometimes good power, sometimes they may be providing, that means less power. That means we can say a variable power is provided to the SCET in wind system, and here it is provided continuously to this generator. And this is the wind turbine. That means here the property of the sources are different. That's why this is one different configuration, and people can work over here. And this is the permanent magnet BLDC generator, right? And then diode rectifier. Power is, you can say, they are rectified and then maintain DC voltage, and then battery energy system, and again the same thing. And this part is more or less same. This is another configuration where a wind turbine is connected through BMSG. That means here generator is changed. It will again provide some, because the nature of the PMSG and nature of the SCET, again they are different, right? That's why there is one more configuration. If you are changing the generator, configuration will be different one. Fundamentals remains more or less same, but you can claim, yes, you have done some different configuration in the microgrid. These are some one source based power generations. Suppose this is the generator of SCET, single phase generation. Only this switches, 4 switches are required in this case. There may be the need of some dump controllers. RD means dump load. It is connected through the chopper. Once battery is fully charged, chopper is on, and extra energy will be thrown towards the RD. These are some configurations based on only only wind generation. These are the you can say topologies of the different microgrid. Here this is 3-phase 3-wire system. This is 3-phase with 2 capacitors system. Single 3-phase. This is overall 3-phase, but units are made from the single phase. These are having some advantages, merits, demerits. Some topologies based on isolated topology. Some topologies are based on non-isolated topology. Suppose this is isolated topology. The importance, the advantage of isolated topology is DC link requirement will be less because we are using the transformer here. You can increase or decrease the voltage level of this side through proper turns ratio of this transformer, accordingly you will get we can say less DC link. And the important thing is, if we are working at lower voltage side at the DC link during the experimentation or during the control side of this VSC, if voltage of the DC link is less, it is easy to manage, it is easy to regulate. Again, these are the isolated topology, and where only four switches are used, two capacitors. Only need is we have to maintain the balanced capacitor voltage of these two. Here it is non-isolated topology, but used for neutral current compensation, because this is the 4-wire terminology. This is also the 4-wire topology. So these are some common topologies where people can work in their research work, in their PhD, and they can publish good papers. They can file the patents if something new is claimed. Now, the research scopes in microgrid. Despite an extensive research, the following topics are still open problems in microgrid. Microgrid is not new actually. There are so many things already people have published, and if we see the literatures, it is not easy to find the gap, but still the work is going on continuously, improving robust performance and stability against the structured and unstructured uncertainties, right? Enhancing the transient response of the closed loop systems. These are the scopes where you can work in this area, accounting for the imbalance and harmonics like neutral current compensation and harmonic elimination. These are the topics belonging to this point. Improving the scalability of the control framework. Suppose somebody is working at low voltage level, you can scale up it and control. You can design the control for that scalable system. Incorporating the DC side dynamics in the control synthesis. As we know, DC side of the inverter should be stable. Otherwise, what will happen? Nothing and no desired response will be achieved. Suppose if we want to maintain the proper power flow, active power flow, it will be difficult to maintain. If we want to balance the reactive power flow different among the various elements, it will be difficult to maintain. That's why DC link fluctuations should not be there in the system. Enhancing the fault right through capabilities. A fault right through is altogether different problem, and you can work in this area also. Basically, power system people are working in this area. They are working in the fault right through conditions and capabilities of different generators. Unified control schemes for both grid connected and islanded operation modes. Right? Control is very big area. There are so many control strategies available in the literature, and if we see all those control strategies, sometimes we confused which one is better, which one is not better. Providing a smooth transition from the islanded to grid connected mode. All these things are dependent on some type of control techniques, and control part is very important. And basically, most of the researchers
Hello, Ashutosh sir, are you there? Hello. Okay. Might be some internet issue.
Hello, am I audible?
Yes, sir. Yes, sir.
Actually, my internet connection, perhaps it may be disconnected for time
Okay,
being.
sir. Okay, no problem, sir.
Now I am sharing once again. Sorry for this. From where I disconnected? Hello.
Sir, you were discussing something about the unified control schemes for grid connected and islanded one.
Thank you very much. Thank you. Now we were discussing the research scope. What are the various research scopes in the micro?
Hello, sir.
Sir, yes.
Your audio is not very clear. Hello, Ashutosh ji, your audio is not very clear. It is fluctuating.
You can work in this area. Basically, my intention was
Hello,
to
Ashutosh
share
ji.
the experience about
Hello,
how
Ashutosh
most of the
ji.
people in academia, when they are starting their research, like PhD
Hello,
or
Ashutosh sir.
MPhil, mostly they are
Hello,
working in
Ashutosh
the
sir. Your
control
voice is not clear.
area. Because topology we cannot change it every time. Yes, I understand, sir. Okay. Hello, am I audible now? Hello.
Yes, sir, you are audible.
Yes, sir.
Okay, whenever there may be some internet issues in my institute, whenever I am not audible, please tell me immediately. Otherwise,
Okay, sir.
once I start my presentation, I am unable to see whether I am connected or not. Right?
Okay, sir.
Now we were discussing the research scopes. I hope so. Now I am clear. My voice is clear.
Yes, sir.
Yes, sir.
Okay. Thank you very much. Now, we were discussing about the research scopes in the microgrid area. Most of the researchers in academia, they are pursuing their research in the control domain, and we must know some basics philosophy of the control algorithms and how to utilize a particular control algorithm in any particular application. What kind of response we are expecting from the control algorithm? All these things we can learn from the available literatures. We can see some response of the other researchers, how they are getting the particular response of the frequency, how they are getting the settling time in the voltage, DC link settling time. All these things we can learn from the available research, and then we can choose one control algorithm. Either it is lying in the classical domain, or it is lying in the artificial neural network domain, or it is lying in the adaptive domain. We can pursue any control algorithm for our work. Now the control algorithms for the microgrid, though the conventional techniques can resolve most of these issues, the issues which we discussed earlier. However, intelligent techniques usually provide more robust solutions, such as very low value of steady state error. All these important indices of the control system, lower settling time and all, right? Suppose your DC link is fluctuated, then how fast it is again going to settle. That means number of cycles are very much important. Suppose somebody is claiming their DC link is settled within 3 cycles, and if you are claiming your DC link is settled within 2 cycles, now the difference is only 1 cycle. You can understand 1 cycle time is not much large, but your claim will be enough to do some publications in good journals, right? Now, some intelligent control algorithms, as far as microgrid is concerned, we all know the given smaller size, lower inertia, involvement of power electronic interface DG, and the limited smoothing of demand spikes, microgrid applications may face significant control, stability, power quality, and security challenges. All these are the challenges. That's why some good control algorithm or intelligent control algorithms are needed to address all the challenges like power quality, stability, security. All the challenges can be addressed. The reason is, in microgrid, inertia is very, you can say, lower, right? In conventional system, the important thing is inertia is very high. That's why frequency fluctuations are not seen quite often. Frequency fluctuation may occur after 1 hour for 1 or 2 seconds. Then again, it will remain same for remaining 1 hour, 2 hour. That's why in conventional system, this is not a problem of frequency or even voltage fluctuations, right? Sometimes voltage fluctuate, but it is not for quite often. But in microgrid, because smaller size and lower inertia, so all these things will fluctuate whenever any disturbance on the load will come. That's why control should be very intelligent to address the things or to correct the things within 1 or 2 cycles. Otherwise, what will happen if you are allowing the disturbance for 5 to 10 cycles? Your control, your protection system may fail, your other devices may fail in the microgrid. That's why importance of intelligent control algorithm is there in the microgrid. It is important to quantify and analyze the challenges and implement the appropriate control system to manage them. The institutions of electronics and electrical engineers, IEEE, as we know, this is the you can say standard which classifies the functions of microgrid control into 3 categories. Basically, this is you can say provisional standards. Still people are working, IEEE societies are working to define the microgrid codes and you can say standards, but these are the provisional standards, and they have said like we have to use this kind of controls. Device level control is known as primary control, local area control and supervisory control is known as secondary control, and grid interactive control is tertiary control. Suppose control. Suppose if you want to make the that means entire microgrid connection from any external grid, or you can say with large intensity, then tertiary control is also needed. Otherwise, primary and secondary control, they are sufficient to control the microgrid. If you are working in the standalone mode, tertiary control is we can say not needed. Primary control, what it functions, what are the functions of the primary control? Active and reactive power control, voltage and frequency control. As I told you, voltage frequency control in standalone operation is very important, which are usually performed in the microsecond to second range. Harmonics compensation, power quality issues, load balancing is also one very important aspect. Suppose there are three components working with the microgrid. Suppose at PCC you have connected battery. Suppose at PCC you have connected solar source. At the same PCC you have connected another source. Then there must be power balance, and suppose load will be naturally there. Load balancing is one very good aspect. That's why these are the things coming under the primary control issues, and they can be solved at the control algorithm, or you can say control techniques, which will be implementing at the device level, right? Keep in mind, primary control means we are developing everything for a particular device. Suppose there are two inverters, you have to use two primary controls. This control is based on local measurement of the electrical parameters. Suppose load current you can measure, you can feed to the control system, supply current, generator current, grid is not there, compensator current, all these things can be measured locally and control parameters can be adjusted accordingly. The most common primary control strategies are droop control and virtual impedance based methods, right? Droop control means it is for the adjustment of frequency, voltage, reactive power, and frequency and active power, P and F, and V and Q. The secondary control performs the functions such as energy management, economic dispatch, automatic generation control, spinning reserves, resynchronization, and fast load shedding, which usually take a time span longer than a second and involve communication. Basically, the secondary control works in the communication, and secondary control can be implemented through either centralized or decentralized control. Model predictive control, we have heard the name of the, somebody may have heard the name of the model predictive control, multi-agent based control, droop control, probabilistic. There are something common between primary and secondary control. There is no demarcation, there is no line between the primary and secondary control. Sometimes the techniques which are working in the primary control, that can also work in the secondary type of control in the microgrid. But tertiary is totally different. Tertiary includes the functions related to market participation. That's why I was telling, if grid is working in the standalone mode, all these things will be absent. Energy exchange with the utility grid and coordination of multiple microgrids. Supervisory control SCADA system is considered to constitute the tertiary control of microgrid. SCADA and energy management system are also usually considered as interchangeable terms, right? All these things are coming under the tertiary control. Now we will discuss here some intelligent adaptive controllers working as a primary control in the microgrid. So this is the basic philosophy, basic principle of intelligent adaptive control. There is one basic philosophy of Adaline control algorithm that I am discussing here. It is available in the books, and this is also not new, but there are so many variants available of the Adaline, and people can work. There are so many things incorporated for making the control algorithms adaptive. We can incorporate all those things in our research and we can carry. But the important thing is we must know the basic philosophy of any control algorithm, how they are working. In any control algorithm, we all know there are some desired signal and there are some output signal, right? And output and desired are producing the error signal. If input signal is given to the filter, and filter means there is one filtering action. Basically, there are three things in the Adaline summary. You can say here first, input, output. Output is known as filter output. Input is tab weight vector, Wn, input vector Xn. That means this is the input quantity which you have sensed, and desired output is Dn. So all these are the terminology Wn, Xn, Dn, and then tab weight vector Wn plus 1. It is updated, that's why it is written Wn plus 1. And what are the three steps in any filter? Either you are using adaptive or intelligent filters. We have to see the filtering, error estimations, and tab weight vector adaptation. So filtering is nothing but it is producing one output which is multiplied by the weight, tab weight, and input of that vector. So yn is equals to omega n transpose into xn. Xn is the input quantity that may be sensed from the sensors, and w is one kind of weight, or you can say, because if we talk about the neural network terminology, it may be the synoptic weights. And then in the second step, error estimation. We are taking the error of the desired and actual, and this error is minimized by using this convergence equation. And this is very important convergence equation, and this equation is also known as tab weight vector adaptation. Omega n plus 1 equals to omega n plus 2 mu e. En means error which is calculated previously, and then xn, right? And our philosophy to minimize the error by using the least mean square principle, and once error will be zero, right, by utilizing the least mean principle, least square mean principle, once error becomes zero, your tab weight vector in the updated and previous, they both will be equal, and then we will say there is one convergence in the weight, and the final weight has arrived. And then with some regression model, we can use the output and then desired, and finally we will get the weight ultimately, right? And this philosophy, these three steps will be utilized in the microgrid. Now the important thing is there are a lot of mathematics. Basically the people who are working in pure control, they are much better in understanding of these mathematics, but we are borrowing mathematics and we are directly implementing in our system. We must know how to utilize these three equations for voltage control, for frequency control, for harmonic elimination, for load balancing. We must know how to utilize all these three equations, right? So being a power electronics engineer, our task is not to formulate, or you can say not to make equations, but our task is to use those equations which are available in the mathematics in our area, in our for our desired results. Now here you can say this is the one philosophy of adaptation, how to adapt the weights. This is the input, and these are some sampling instants, right? You are getting, suppose by some delay, you are getting xn minus 1. After further delay, you are getting xn minus 2, and finally at nth delay you are getting xn minus n plus 1, right? And these are the synoptic weights. You can say these are the omega 0, omega 1, omega n minus 1. Initial weights are defined first, and then you are giving the x signal, input signal. Input signal may be, in our case, it may be the load current. Suppose if we want to compensate the load side, suppose harmonics are there in the load, suppose power quality related problems, because power quality problems are created from the load side. That's why load current may be our interest, and suppose if power quality is created from the supply side, then supply voltage may be the quantity of interest. Suppose here we are discussing the compensations for the current, and then the Xn will be the load current, and accordingly you will set these quantities in between 0 and 1. Initial values you have to choose. Initialization may be done for these weights, and then finally you will multiply X and W, you will get some value over here. Similarly, you will multiply Xn minus N into W1, then you will get another value over here. All these will be the output of these you can say these weights, right? And finally all those outputs will be added to get the desired output Yn, and you have already set the desired level of the output. Then actual output and desired output will be taken difference, and then finally you will get the error, and error will be minimized by using some kind of least mean square adaptation techniques. And finally these weights will be adjusted according to the error, and finally you will get again another weight. Suppose error is large, these weights will be updated from this equation, and again they will be multiplied by the available input. You will get another Y actual value, and it may be closer to the desired level, error may be smaller. That means this process will continue till Yn is not matching the Dn, right? So this is one adaptation basic philosophy, how adaptive filter is working, adaptation is working in the control algorithm. Now this is one implementation of the control algorithm, how to implement for power quality features, for getting the harmonic elimination, load balancing, all those points. Suppose at PCC some sources are connected, how to get the proper load balance among the sources. PCC load is connected, it is creating problems for the generation side to eliminate the harmonics for the load. So all these this is the basic theory, and this theory is utilized for generation of the control signals, and I hope so you are getting this. Is it visible?
Yes, sir. It is visible.
Okay.
Yes, sir.
Now, yeah, fine. Now, as I was telling, our DC link must be stabilized. If DC link is fluctuating, no control will work, right? Because we are designing control for the device. Device is inverter, and we are generating some control signals for the inverter. And the thing is, first of all, we must have some reference value of the DC link. Basically, if we are working for 220 volt, suppose, for example, a three-phase 220, if I say at the AC side, or suppose some objection is there for taking three-phase 220, you can take three-phase 440. Any value you can take at the AC side, and then inverter DC, you have to take a reference 1.6 times higher, right? Suppose we are working 400 volt AC side, then almost 700 something, almost 700, 695 or something may be the reference at the DC side, right? That means at least that value you have to maintain for proper operation of the device. Otherwise, there will not be any effective control, voltage control or frequency control or power balancing. Nothing will be obtained if your DC is going below 700 volt. That's why DC reference is needed, and actual DC you have to sense, and then it should be compared. Then using PI controller, sometimes you can use some optimal controller also here. Basically, I have used PI controller, basic PI, and all this PI controller will generate will try to minimize the error between the DC reference and DC actual, right? Now the important thing is over here. What are these blocks? This is one block. It is creating a weight for active component of the load current. Basically, we all know in the load side, if any load current is injected at the PCC, it will be having two components, active as well as reactive, right? And we want to supply active components from the sources, right? Suppose if you have injecting currents from the solar side, there should not be any kind injection of the reactive part. There should always be injection from the solar side, active component only. Similarly, if we have connected any generator from the microgrid, generator always supply the fundamental component. If it is supplying fundamental component, 50 hertz component with almost in phase with the supply voltage, we can say yes, it is supplying only active component to the microgrid. And that is the need. That's why we are segregating here. And whatever the requirement at the PCC, the reactive power requirement at the PCC should be entirely taken care by the device itself. Device means our inverter, right? That's why we are segregating load component in two parts, active as well as reactive, right? And for implementing the control algorithm for the active part, the same equation what I discussed, the third point. First one was filtering, second was error estimation, and third one was tab weight vector adaptation. So we are using here the third component, third equation, tab weight vector adaptation. This is the WPA, means active of phase A. This is, here we have written K. Sometimes you can write K plus 1, then you will write here K. If you are writing K, you have to write here K minus 1 plus eta ILA. Yes, I was telling you in the error, this is the error actually. This is the error part. ILA minus WP K minus 1 and UPAK. UP means what? This is the template, active phase template, right? This is the pure sinusoidal component with magnitude of unity, right? That's why it is used here, UPAK, and then finally UPAK. Again, it is the magnitude unity template, pure sinusoidal template. And estimated reference value is nothing but once it is convergent weight, that means if error becomes 0, then finally you are getting the WP and multiplied by UPA, you will get the reference point for the inverter. So this is one philosophy, how to get the active reference from the three equations. Error calculation, that means filtering. Filtering means multiplication of this and this. And error calculation means actual minus, this is ILA. ILA means actual minus this one, right? And this is one learning coefficient. We have to choose some value for this learning coefficient in between 0 and 1. Eta is known as learning rate, basically, right? We can keep here some value from 0 to 1, and accordingly this convergent equation will start. And after getting the convergent weight, we can calculate the reference for the phase A. Similarly, this is the active weight equation for phase B, and this is the active weight equation for phase C. And the back inputs, or you can say feedbacks, are coming according to the requirement in the equation. Suppose WPA is needed, WP is needed, ILA is needed, and UPA is needed, right? UPA, UQA, UPB, UQB, UPC, UQC, all these unit templates can be calculated. I will discuss it later on also. They are calculated from this block diagram. Basically, for the calculation of templates, supply voltages are needed, VA, VB, VC, right? And then there is one equation to calculate the magnitude of the PCC, magnitude of the voltage. That equation is square root of 2 by 3 VSA square plus VSB square plus VSC square. Once VT is known from this computational block, divide VSA divided by VT, you will get UPA. It is simple. Vm sin omega t is the supply wave. If we are dividing by Vm sin omega t divided by Vm becomes sin omega t, and sin omega t is nothing but unit template of fundamental frequency. The same thing we are doing here with the available three voltages. We are calculating the terminal voltage VT. Terminal voltage VT is calculated from that relation. It is available in the literatures. Even in my papers also I have given in detail. UPA, UPV, UPC are calculated, and then quadrature components. There is one matrix which will transform the in phase components into the quadrature components. UPA, UPV, UPC, with the help of equations, it will be calculated. Similarly, this VT is calculated, what I was telling, because VT is nothing but under root 2 by 3 VSA square plus VSB square plus VSC square. And the same VT which is calculated over here, it is divided here, VSA divided by VT, right? All these templates you are getting from these two blocks, and these templates are used here. Similarly, VT is calculated and VT reference is set. VT reference is set. Suppose we must know the VT reference for our grid PCC. What should be the VT reference? Microgrid PCC, right? Suppose in case if I say this is the 220 volt microgrid PCC. Suppose we want to maintain 220 volt at the grid, then almost 195 or yes, 195. You can do the calculation as well. I have done it, and that's why I'm telling the value. 195 volt will be set as the reference. Suppose you are doing the simulation and you are not setting the proper value over here, it will never produce the desired result. That's why DC reference and VT reference, they are playing a pivotal role in entire control algorithm, right? So you don't take reference values very randomly. Yes, if suppose 197 is the exact calculation, and if you are setting 200 volt, that may work. But suppose 197 is the actual requirement and you are setting 120, 100, 400, then it will never work, right? So all these blocks are giving the weights for active, weights for phase A active, phase B active, phase C active. All three weights are added and they are averaged. Averaging is done for the power balancing, right? And similarly, reactive weights are calculated. Reactive weights are added over here and they are averaged with this VT, right? And 1 by 3 is divided. And then finally, we are getting phase A active and then phase A reactive from this one. And they are added to get the one reference current of phase A. Similarly, reference current for phase B, reference current for phase C, and then actual current is sensed, and finally they are compared and they are fed with one modulating signal to the PWM controller. It may be hysteresis controller also, and finally you will get the current pulses, or you can say gate pulses for the inverter circuit. And remaining operation, that means whatever you have set over here, accordingly your inverter will work and control the microgrid operation. So this is all about the Adaline philosophy, how to utilize the Adaline control, how to use these three things. Basic philosophy in any Adaline or in any adaptive control is these three: filtering, error estimation, and tap weight vector adaptation, right? We must know how to utilize this. And then back propagation feed forward network controller. This is another class of control, and this is also very nice one. And they are producing the results within you can say within 1 or 2 cycles. We have seen in hardware implementation all these algorithms we have implemented. So this is the back propagation feed forward based control, regulates voltage and frequency of the microgrid. In this scheme, multi-layered feed-forward network consists of input layer, hidden layer, and output layer. We all know the neural concept. Powers, even the people who are working in the power group or power system group, they may be using some neural networks. That neurons may be we can say kept at the input layer, hidden layer, and output layer. They are interacting with each other. The input signals passes in feed forward direction from input layer towards the output layer on layer by layer basis, right? Signal flow is from input to output side, and supervised learning with back propagation algorithm is used here, which works on the error correction learning rules to achieve. Now you see here the error correction learning rules to achieve the desired output. Ultimately, the third equation which that was using here, the similar kind of equation we are using in the error correction mode in the neural network also, right? Now we will see some philosophy of the back propagation. This is second control what I want to show here. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now 3 layers. The first layer is input, and then hidden, and then output layer are taken to realize the control. The input layer neurons in its first half portion as a aggregation function. We can write for active and reactive components like this. ILPA equals to initial weight of the synapse, synaptic weight, we can say this is the initial weight. ILA is the load current of phase A. UPA is the unit template of phase A. ILB. Now these terms you may be familiar from the previous control algorithm. UPA means unit template of phase A, then unit template, active unit template or in phase unit template of phase B, and this is the ILB, this is the UPC ILC. So ILPA is calculated like this. Similarly, ILQB, active and reactive, these two components are coming from the load current, right? And then W is plus ILA UQA. Instead of UPA, we are using UQA, right? And things are now understandable here. These values are passed through the second part as activation function of the input neurons. We all know in the neuron, after the core of the nucleus of the neuron, there is one activation function. Sometimes we are taking exponential, sometimes people are taking sigmoid, sometimes people are taking linear, sometimes people are taking step functions as an activation function. Here it is taken as a sigmoid function, and the output of the input layer neuron for phase A becomes XPA. That means after the activation function, if we are taking the sigmoid function, XPA is the quantity coming out from there, 1 upon 1 plus e raised minus ILPA, and similarly for QA. And these input layer outputs are fed to the input node of the hidden layer, and aggregation function of this layer is expressed as this W1, because now for the next layer of the neuron, this is the input, right? Initially, what was the input at the input layer? This was the template was the input, right? Now we are getting and current was the input. Template and current, they were working as an input of the first layer, but output of the first layer is working as input for the second layer, right? That's why we are getting here W1 plus WPA. This is the weight coming from the first one. Synaptic weight is now changed, and then XPA is the quantity at the place of template, right, after the sigmoid function. Then WPB XPB plus WPC XPC. Similarly for the reactive component we can get, right, where W1 WPA PB PC are some constant values from 0 to 1. All these values are coming in between 0 to 1 to initialize the weights. These values are updated by back propagation error correction rule, and this is the error correction rule, right? In this error correction rule, we can see here WPAR equals to WPTR plus eta. Learning rate, again it is coming, and the same thing what we have discussed in the previous slide. the learning rule, more or less, they are same. This is the, we can say, a convergence equation for getting the updated weight. All the synoptic weights are updated to get the desired output, right? And then again, sigmoid functions after the second layer, we are getting this kind of relation, right? And then amplitude of the fundamental active power component of the load current is averaged. All three are averaged for the balance operation. Averaging is done for properly for getting the balance operation. So WPT and WQT final averaging is done, and now this kind of control is implemented in with the help of block diagram. All these things with the help of equations you have already we have discussed it already. And what are the inputs requirement? ILA, ILB, ILC, PT, QT, WPT, QT, ILA, ILB, LC, and basically we are getting here PAL, QAL, PBL, QBL, PCL, and final updates of the neuron. And finally, they are taken the you can say averaging over here 1/3, and for eliminating some you can say higher order harmonics during this operations, there may be some oscillatory components generated. They can be eliminated by using the LPF of you can say 10 radian per second or 15 radian per second, so that pure DC component will be coming over here, and finally they will be multiplied by the again sinusoidal components, because these are the DC components. DC components will be multiplied by the templates, again they will become sinusoidal components, and you will get ISA, ISB, ISC sinusoidal reference over here. These are the actual components of the supply current, ISA, ISB, ISC, right? And supply means I am talking about the currents which is injected from the supply side towards the PCC, right? So these are the things, and finally pulses are generated, and you will get the pulses for the inverter. So this is one control algorithm, and this is one another class of control algorithm. This is based on LMS square, least mean square principle, and momentum term is involved over here. So basically, if you see, this is the similar equation, but only this difference is there. Epsilon ZPK minus ZPK minus 1. This is the error between previous weight and updated weight, and that error is taken to accelerate the convergence process. Just this error is multiplied by the epsilon, that is the, you can say, momentum factor, right? It is like similarity is coming from the, drawn from the Newton-Raphson technique, right? In the Newton-Raphson techniques also this kind of philosophy is used. We may be knowing x1 equals to x0 plus delta x, right? The similar things we are using here. ZPA, ZPB, ZPC are the active components. QA, QB, QC. Averaging is done, and then frequency. Suppose reference frequency and then actual sense frequency. They are estimated. Component is, that means current component from this current controller is created, and finally multiplier. Remaining part is same as previous one. And what I was telling here, the equation is given VT equals to 0.666. 0.66 means 2/3. VSI square plus VSB square plus VSC square. And then XPA means UPA. Unit templates are calculated over here. And then quadrature components can be generated from the matrix. And this is the reference and signal generation for microgrid control with DPLL technique. That means differential PLL technique, right? It is another technique, and we can use it. By this DPLL, we are able to fetch the fundamentals of the load current directly, right? Frequency lock, then phase lock, and then harmonic isolation. and the details of these 3 steps are discussed over here, right? And finally, again, we are getting different components, suppose solar, wind and all, and this IF is calculated from the load current. That means this is the process of fetching the fundamental from the load current, right? Where the space phasor is created first, then real imaginary is bifurcated, then tan inverse, then estimated value of theta actual from the load current. Then this is the matrix, or you can say gain, HZ, and then radian frequency is estimated, then integrated, then actual theta 1 is coming. All these things you can do, and then finally gate pulses are created. And these are the effectiveness of the phase angle estimation. It is shown here. Suppose how effectively it is matching with the you can say the disturbance. Suppose here there was their input and output current, they are matching to each other. Here some disturbance is created, then current is also settling within very less time. Again it is matching over here, right? And this is the phase angle variation during entire disturbance. This is the theta error graph and theta 2 estimation. And one more, a neural network based radial basis function control algorithm. You may have heard the name. Again the similar things are given. Only thing is, this philosophy you must understand, this is the third equation of the adaptation, right? And this is the function of sigmoid. ILP alpha AP is calculated with the help of this function. ILP is calculated from the previous control algorithm. You can understand how ILP is calculated, and then sigmoid is used, and finally different adaptation equations are used in active and reactive. And then normalization process using LPF and taking some gains over here, then finally everything remains same. Now these are some simulation results. We are discussing about the VT variations. VT, this is load is rejected and how fast VT is settling, right? VT means terminal voltage of the grid, right? And these are the UPA, UQA, fundamental calculations of the load current and phase angle estimations. All these things are given here. And this is the dynamic performance of highlighted microgrid during the variations in the wind velocity. Suppose wind is changed over here, what will be the variations in the supply current, supply voltage? We can see here there is no, if we see here the envelope of the voltage, there is no change in the voltage level, right? Current level may be changing due to variation in the wind from the generation side, but there is no change over the voltage level, right? And this is the compensator current. Frequency, yes, frequency is important parameter to watch. Now if we are changing the wind speed, frequency may be fluctuating, but it is settling very fast. So these are the some expected result. Suppose dynamic performance during variation in the solar intensity and unbalanced load. Then suppose this was the solar intensity, initially it was around 900. Now it is changed over 2.8. It may be around 600. Then temperature variations is happening accordingly. Reduction in the PV current is happening accordingly, and then reduction in the PV power is as well, right? Reduction in the duty cycle. All these things we can see just by changing the insulation level. And now in this graph we can see here the reduction in the CPI current, right? Change in the insulation level, and then finally we can see here, and charging current of the battery dynamics you can see in this graph. Reduction in the CPI current. Load unbalance is also created, but we can see here load is not linear, but still we are getting the linear current. That's why power quality is better. Power quality, what we are expecting here, the current drawn from the generator side in the microgrid should be sinusoidal. That should not be distorted. Here load current, we can see clearly it is like power system insulator, right? It is not sinusoidal current, but we are getting the sinusoidal current over here. This is the load rejection over here, and again load is injected, and we can see the changes in the compensator side. This is the device control, basically what we have used as a primary control. Device control, primary control is managing everything: voltage level control, frequency level control, power balance operation. Power balancing is done in the battery. All these VDC you can see here. VDC is fluctuating very small. Some smaller fluctuations may be persisting for some cycle, but basically it is not out of control, right? We are managing it within the constraints. Similarly, here some comparative performance of different control algorithms are provided just for your reference. Basically, these results is still under some review process. We have submitted it, but I am showing here for the sake of clarity, and we can see here the load rejection, and we can see here how it is coming, how we are managing the load inclusion. Things are settling within a second, microsecond. Things are given over here, and these are some adaptive controls. Comparison is over here. Suppose this is the adaptive vectorial filter, momentum LMS control, what we have discussed here, non-linear adaptive Volterra filter. This is the Lorentzian adaptive filter. This is the VCOLS PLL. All controls are just compared on a single platform. Single platform means we are taking the constant load, and load is disturbed over here, and we have observed how the control is performing for maintaining the terminal voltage and frequency. So you can see the comparative analysis over here, how different controls are working well. Now these are some observed results from this diagram. We have read from the MATLAB, and we are plotted over here. These are the control algorithms. They are giving settling time, steady state error by this way, and from this we can select which one is more suitable. From this study we can select which one is more suitable for our application according to these indices of the control: settling time, steady state error, and then sampling time requirement, right? Now, design and development of the MG prototype for laboratory experiment. Hello, am I audible?
Yes, sir.
Yes, sir.
Okay. Will you allow me to discuss this?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
That would be fine.
Okay. Design and development of the microgrid prototype for a laboratory experiment. What are the various components required for the microgrid development? Basically, this is one laboratory setup what I made in the SVNIT Surat. We are this is the basically I have not given the list of the setup, but I am telling this is the generator motor set, basically used for wind generation side, and this is the drive ACS 550. This drive is used to emulate the wind turbine like conditions, right? For the motor, it is the programmable device. We were able to program it for oscillatory and de-oscillatory mode of the motor. Suppose we were generating some oscillations at the motor terminal. Accordingly, generator was oscillating, and we were getting the frequency fluctuation from the generator side, right? So this is the emulator. It is working like a wind. Wind is fluctuating. Similarly, emulator will create conditions like wind fluctuations. And these are some auxiliary operators. This is you all are knowing it. This is not needed to tell here. And these are the switches. These are the capacitor banks for excitation purpose. And these are the instrumentation devices like power quality meter. Actually, this is the sensor circuit. There are 3 story over here. One is the one story contains DC supply. The second story, we can say sensors are laid down, and at the top of the this rack we are keeping the devices, circuit breakers and all, and then interfacing inductors are kept. All these are the components like interfacing inductor, multi winding transformers. Sometimes we are using transformer also for passive compensation in microgrid. Then we are using the transformer. This is bigger inductor to create the distortion level. Suppose because in the laboratory prototype you have to create the conditions like actual conditions. In actual condition, non-linear loads like chargers, laptop chargers, mobile chargers, television sets, they are creating the distortion problems for the supply. Similarly, here we are keeping inductor. Inductor will create some level of distortion. Suppose after diode, if we are keeping RL circuit, then definitely we will get the distorted current. These are the loads, and these are the lamp loads, basically treated as a resistive load. And yes, now this was the power circuit, right? And in fact, this is the converter. That means this is the 4-leg converter. You can see here the terminals, red, blue, green terminals, and 3 points are taken over here. We have made the PCC over the top of this rack, right? PCC means point of common coupling, from where generator and supply terminals of the load, generator terminals, supply terminals, load terminals and compensator terminals are connected over here. And this is the controller part. Basically, this control is the controller is DSpace 1104. This was the basic controller. It is not too much costly, costing around 6 lakhs. Nowadays we have in the laboratory like Microlab box also, it is costing almost 14-15 lakhs. That is costly. But the flexibility in the Microlab box is much better than this DSpace, because in DSpace only 8 ADCs are provided. Suppose if you want to sense the 9th signal, you will not be able to sense it, because ADCs are not there in the this one. Then we have to manipulate it by using additional control techniques. In the control side, we have to do some mathematics to adjust the signals, or sensorless we can say. And these are the devices. This is the DSO used for measurement. DSpace is a very important, or you can say major component of entire setup, right? There can be different different session on the DSpace. It will take 2-3 hours for entire explanation. How we are managing the DSpace operation, control desk operation, how we are refining the parameters, because monitoring, correction, measurement, there are 3 things simultaneously can be performed using DSpace, right? Now this is the inverter. You can see the better picture over here. There are 4 legs, 1, 2, 3, 4, right? These are the inbuilt circuits. This is our battery, 220 volt, 110 volt and 400 volt terminals are given. This is the DSpace. The close view is here, and this is the excitation capacitor motor generator set, and the design of voltage sensors circuits are there, right? We were designing that means we were discussing over here, sensor are laid. This is very difficult process. It is not an easy task, right? We have to do everything mathematically, and then we have to measure, and finally sometimes corrections are also needed. So this is the design of voltage sensor. How to design it? We have to see first data sheet. According to the data sheet, we have to keep these 2 resistances. Calculation is calculation must be very proper. Otherwise, what will happen? That the sensor signal is going towards the D space, right? BNC cable. You can see here these cables. These cables are known as BNC cables, and these are the ADCs. 8 ADCs and 4 DACs are provided here. ADCs are binary in nature. They can tackle signals from minus to plus. It is not like STM32 ADCs where you have to take some offset. Here no need to incorporate the value of offset. It will tackle the signal in both directions. Sampling will be in both directions, but the important thing is its limitation, minus 10 to plus 10. Suppose your sensor you are not properly designing. Suppose you have not properly designed, randomly you are keeping the values over here. Then it may give the output more than 10 volt, and then at that time your ADC will go, right? And once ADCs will go, this space will be no longer in use. That's why it is very important. It is very, that means we have to take extra care to design the sensor, voltage sensors and current sensors. How to design it? As per the data sheet of the low voltage LV 25P. LV 25P is the model. Each sensor or transducer is having rated current transformation ratio of 10 milliamps to 25 amps and 500 volt input voltage rating. That means what? We cannot keep more than 500 volt over here, and input and output current, that means from this terminal and from this terminal, current is given in the data sheet 10 to 25 milliampere transformation, current transformation ratio. That's why input side maximum 10 milliampere can flow. If you are flowing more than 10 milliampere, what will happen? This sensor will go, right? So R input is required. Basically, you are designing the R input. What should be the value of R input so that after application of 500 volt, input current should be less than 10 milliamps. So this is the requirement. That's why we are doing calculations over here. And R input equals to 500 volt divided by 10 milliamps. Accordingly, you will get, this is very simple relation. R equals to V by I, and we will get 50 kilo. Power rating 500, V square by R, simply V square by R, and power rating you will get 5 watt. So you have to choose the input resistor value of 5 kilo ohm, 5 watt, right? In the market, it is available. Now, in order to obtain the output voltage near 5 volt, why we are keeping 5 volt over here? Because as I told you, 10 volt plus minus is the limitation value, limiting value of the ADC of the D space. That's why we are taking 50% of that 0. Again, 5 volt is the set value. We are setting it externally. Somebody may design for 7 volt also, but for any correction, if 7 volt is going to 9 volt, you are going very closer towards the limit of the DSO, D space. That's why we should be very careful. 50% margin is given. That's why V0 by I0, 5 by 25 and 200 ohms is the value. But suppose what I told earlier, correction will always be there. 200 ohm may not be available in the market. Suppose you are going to market and this value is not available, but 270 value is available. Then you have to select 270 and accordingly correction will be made. And if you are doing the further correction, your value is moving towards 7 volt. Just you see here. That's why if you are choosing already 7 volt, you may be moving towards 9.7. So that's why proper margin must be there for the D space operation, right? And accordingly, power rating will be calculated as per 270 ohm. Here V square by R, and because new value of the voltage will be taken, V square V into V by 270, and this will be the power rating, right? By this way, this value will be selected. Design of current sensors. In current sensors, this is the hollow space where wires are wrapped, right? In the voltage sensors, there will not be any hollow space. I will show the figures. I hope so. I have given here somewhere. Yes, you can see these are the current sensors, right? And these are the voltage sensors. These are I personally made in my laboratory during my research. This is the current sensor through which wires are wrapped. These are the voltage sensors. Now, design of current sensors are equally important because every measurement, load current, supply current, all currents are measured and feedback to the control system through the sensors, right? Sensors are intermediate or interfacing components, are power conditioning components of the entire system. So according to the power rating, a data sheet, again we have to go for the data sheet. If you are working with sensor, you have to keep your data sheet just at your right hand, in your right hand, right? Every time you need to look into the data sheet, what are the current transformations, what are the limiting value of the currents from the primary side, secondary side, all these things will be available in the data sheet, and we have to continuously watch the data sheet, right? And this is the LA55P. LA means this is the ampere, current ampere, and LV, you have seen in the previous one that voltage model was LV. LV means this is for voltage, and LA means this is for current, right? LA55P is provided here with primary winding current. Limitation is rated current value 50 ampere. You cannot flow more than this. And suppose if line current is 10 ampere, then corresponding output current is 10 milliampere, right? Therefore, because 1 is the 1000 is the transformation. Suppose if 1 ampere is 1000 ampere is flowing from the primary side, 1 ampere we will get at the secondary side, right? But transformation is like this, but we cannot flow 1000 ampere from the transducer. The current limit of the transducer is, primary current is limited to 50 ampere only. That's why, and suppose in our setup we are working with 10-15 amperes. If we are designing our sensor resistance value for 10 ampere, then corresponding output current becomes 10 milliamps as per this transformation ratio. In order to calibrate 10 ampere line current as output voltage of 1 volt, the minimum value of the output resistance will be calculated over here, and power rating is 0.01 watt. So selected value is this, right? And this is available, you can see it. This is the photograph of the developed circuit, I already explained. And this is the isolation circuit, design of isolation circuit. Isolation, it is the component kept in between the D space and IGBT, right? Optical isolation is because IGBTs are working at high power level, while D space is working in the loop of you can say we can say D space is working in the loop, while our IGBTs are the part of the power circuit, right? That's why they must be optically isolated, and this is IC 6 and 136 used for the optical isolation, right? This is very simple philosophy. We are giving the gate pulses over here, and there are two different grounds. They are isolated grounds, right? Because this part is now going to connect from the IGBT drivers, and this part is connected from the D space. That means we are getting the ground of the D space over here, while this is the ground of the driver circuit of the IGBT over here. So these two grounds, people what they do, sometimes it is a very big blunder in the laboratory. Sometimes students are keeping both grounds same, and in that what will happen, first of all your driver, this circuit will go, and then your driver, the chances of driver will also that also gets damaged, right? And entire operation of the system will that means affected when your driver is not working. These are some experimental data and experimental results according to different control algorithms we have taken. Basically here the load removal, PV balancing, battery, load removal, current, sinusoidal, nonlinear current, sinusoidal supply current, voltage frequency maintenance. We can see here load is disturbed but frequency and voltage is remains same. All these things are achieved, objectives are achieved by using some control algorithms, and they are very we can say faster, accurate, and we can see here the base dynamics. That base is battery energy storage system used in microgrid, and this is the load injection over here. Then we can see the decrease in the battery charging, we can see the increase in the battery charging after load removal, and still we are maintaining the battery level, VB, battery voltage level. We can see here the compensating currents. Just this, why I'm keeping the waveforms over here for your reference, so that you must know what should be the result, and your fundamental law, that the laws of the fundamental electrical circuit like KCL and KVL, that should be followed over here. You can see here, if any phase is going down, then ISA supply side and compensator side should be the same current, because at PCC there are three components: supply side, load side, and compensator side, right? So if load side is removed, supply side and compensator side should have same current. So by this way, you can see here KCL is also validated, and all these rules. And then transformer is also used for load balancing and neutral current compensation. And this we can power balancing under wind speed variation, we can see here, right? Voltage profile, you can see throughout the PCC it is maintained. And these are the some steady state results. This is the steady state results, and we can see the harmonics in the load current. We can see the harmonics in the supply current. Load current harmonics is almost 34 point something %, but we are getting the harmonics in the supply wave less than 5% as per IEEE standards. So these are some steady state results. Power measurement is done, and standardization, as I earlier said, still work is going on by IEEE. There are societies working in the process of developing specific standards. These standards are given, but still in the literature I have seen standards are not finalized for microgrid. That means topology, as far as which topology will be known in which category, how many sources can be connected for microgrid configuration, what should be the grid code for a particular microgrid. Suppose sources are changed, grid code will be remain same or changed. All these things are under discussion by IEEE. And now these are the references used for this presentation. I have already working on some projects. This is just for reference, and PhD students are also guiding under process. There are 3 students and 2 more vacancies there. I am looking forward. These are the book publications, edited books, and some international collaborations. I am getting some helps from the good people. That is Professor Joseph. Sabir sir may be knowing better. Director and Professor of Chrome, Aalborg University, Denmark, and Professor Vinniko, Tallinn University of Technology, Estonia. And thank you very much. This is all about from my presentation.
Thank you very much, Ashutosh ji. Participants, if you have any query regarding the work that has been done by Dr. Ashutosh, you may raise your queries. I think he would be happy to answer and share his knowledge. He has very well and elaborative explanation of whatever the work he has carried out during and after his PhD work. He has also explained the various sorry for it, various grid connected topologies like wind PV, wind diesel, isolated and non-isolated modes. Apart from that, he has also highlighted some of the uh, research areas available in the microgrid, particularly in the microgrid field. Though he has said that there are so many research work going on across the globe, across the India, but there are still many gaps and which needs to be identified. Apart from that, he has explained the intelligent adaptive adaline control, neural network based control, and those things. And as the icing of the top, that he has also touched the design of the sensor and the significance of the sensor. When we are connecting some intelligent devices, intelligent controller like DSpace or RT lab or micro lab box, and what care needs to be taken, that is an additional information that he has shared with the participants. So I'm very much thankful, Dr. Ashutosh, for your very great and in-depth presentation. Now, if the participants have any question, please, they may ask the question, or meanwhile they are figuring out their confusion and the question. I would like to ask one or two questions, Dr. Ashutosh.
Yes, yes, sure, sir.
As it is a very challenging to transform an algorithm or simulation work into the actual real working prototyping. So that is that
Yes.
you have done. That is very grateful, and that verifies, that validates more clearly the algorithm develop and the simulation work. So in that you have used, you have emulated one wind and the battery storage, if I'm not wrong.
Yeah.
So that PV is not being used in that case.
Yeah, in my case, PV is not being used during my PhD, but now I am using PV as well.
Okay.
That
And
result actually I have not shown here because the results are under some
yes.
circulation.
Yes. And then the algorithm that you had discussed, different algorithms, while comparing those different algorithms. So in that, any MPPT in case of PV or wind is being incorporated or not?
MPPT actually now we are incorporating with the wind generation.
Okay.
And but actually that is totally independent from these algorithms. These algorithms basically used for only weight extraction process.
Okay. Okay.
We are not utilizing the duty cycle calculation.
Yes.
We are using some different terminal, that means algorithm, that those algorithms are not very complex algorithm for creating the duty cycle of the boost converter, which is used in coordination with PV cell.
Yes. And what is the level of power or the power handling that for the setup that you have shown, and how much amount?
3.7 kilowatt.
3.7 kilowatt.
Yeah.
That is for a wind system. And what would be the battery that you have incorporated in it?
400 volt. Battery
400.
level is 400 volt. Yeah.
Okay.
400 volt DC.
So participants, if you have any question, you can take an advantage of such a speaker who has fetched very good amount of the grant, who has been working with the foreign as a foreign collaborator, and has worked extensively in the field of the microgrid and integration of the microgrid with the different controls. So please, if you have any question, you may ask the question, or otherwise we can wind up the session.
I am sharing my email ID to participants. If they have any query or doubt, suppose somebody is working in this area, they can, I may
They
be
can
helping to
contact
them.
they can contact Ashutosh ji directly, or they can ask us and we'll route the question and your queries to the Ashutosh ji.
I hope so participants have enjoyed or not.
Uh, they must have enjoyed. Yes, those who are working, they must have enjoyed.
Yes, yes.
That's why I told you that as at the end of your session you had also explained the sensor, so that is an additional information one would be getting. Otherwise, in such kind of the presentation or such kind of the platform, most of the speakers that talk about the algorithm hardwares, and nobody is interested to explain those kind of small things which are equally important.
Yes, correct.
Sir,
Because that is
really
the heart
good
actually.
session, sir. Sir, it was really good session, and you have done excellent work in this field. Congratulations, sir. Thank you.
Thank you very much. Thank you. But I would be more happy if somebody asks some query. I would like to answer if you have any doubts and problems. Otherwise, I have written my email ID as well as my mobile number. You all are our peer colleagues. You can discuss anytime. I will be happy to help if somebody is working in this domain. And hopefully in future also we will work. That means together. I will be more interested to work with the Dr. Samir sir also.
Sure, sure. I will definitely be in touch with you.
Yeah, yeah,
If
yeah.
you would be if helpful to you, then that is also very great.
Thank you,
So
thank you.
it would be a win-win kind of situation for both of us.
Yes, yes, yes. Thank you, sir.
Okay,
Thank you very much for
thank you
giving
very
me
much.
this wonderful opportunity to present myself over here.
Thank you very much, Ashutosh ji. Thank you.
Thank you. I think so. We should leave.
Yes, you may leave the meeting. No,
Thank you. Thank you
thank
very
you very
much.
much, sir.
Bye bye. Bye bye. Namaskar.
Now all the participants are requested to have a break of 45 minutes. It is almost 1:10, so we'll be meeting again at uh, uh, 2 o'clock, and the session would be on the inertia of the microgrid, and that will be conducted by Dr. Zakir Rathir from the IIT Mumbai. So because of his tight schedule, and his request, we need to schedule it at 2 p.m. instead of 2:30, and he would be taking around 1 to 1.5 hours on the inertia of the microgrid. So I request all the participants to join on time, be on time, because it may be possible that we may not wait for even for a minute due to his busy schedule. So again, I request you to join at 2 p.m. sharp. And thank you very much for listening to these speakers and part of this FDP. Thank you.